Welcome. So this is gonna be your I'm gonna go general physics one. General physics one. So it's gonna be general physics one. And we're gonna be doing chapter two. It's not chapter four, I'm sorry, chapter four from Cutnell and Johnson book, which is going to be forces and Newton's law of motion. So the first thing we want to do is define force. What is a force? So we define a force as a push or a pull. Now, there's two types of forces. You got your contact forces, which they happen from physical contact. And you got action at a distance forces. They do not require contact, such as gravity, for instance. You do not need that, or electrical forces. Now, talking about forces, let's go ahead and open up our little PowerPoint. So force is a push and a pull. Contact forces arise from physical contact. Action at a distance forces do not require contact and includes gravity and electrical forces. Now, the force itself is any influence can cause an object to be accelerated. How does an object can be accelerated? If there was a net force on it or an unbalanced forces on it. Now, because the direction matters, arrows are used to represent forces. They are vectors. The length of the arrow is proportional to the magnitude of the force. So let's go ahead and write that down. So your force is any influence, basically, that can cause an object to be accelerated. And how that happens? By unbalanced forces. So for instance, in the scenario that we have, you got two guys pushing on a block. The question is, which way would the block go? And the answer is whoever has the most force. So if you got this person over here pushes this way and has more force than this person, the block would go that way. If you have, let me get a different color on this. This person has more force than that person, then your block will push in that way. If they both have Balanced forces, same amount of forces going out, so the blocks do not move. And that's what we're talking about, the mass. So the mass of a body is the property of matter that manifests itself as inertia. Now, the greater the object's mass, the greater its inertia. Now, the unit for mass is kilogram. So your mass is the amount of stuff contained in the object. Let's go ahead and write that down. So your mass go ahead and get black. Is a measure of amount of stuff in the object, and the unit for it is your kilograms. That's your international units for mass. Now, going back over here is that we define the mass as, again, the measure of amount of stuff that's in it. And the mass of the body is a property of matter that can manifests itself as inertia. So what is inertia? Well, inertia is the apparent resistance of an object offers to any change in the states of rest of motion. Now let's go ahead and watch this video to help us understand a little bit about inertia.
If a glider is at rest on a track.
If the glider is resting on a track and you shift the track side to side, the glider will move with the track. Now you put cushion of air under the glider, and that means it becomes frictionless surface. So what would happen right now if we shift that bottom side to side? So you got a glider that's on a track, and we put a cushion of air and we slide it side to side. So what would happen? Would it move with the track, remain stationary, accelerate in the direction of motion, accelerate in the opposite direction of the motion relative to the track? All right, let's go ahead and watch the next video to look at the answer. The glider is now motionless. Now, if you give it the opposite, if you give it a single push while the track is stationary, it keeps on going back and forth. Which brings us to Newton's first law. Now, Newton's first law states that an object, if no net force acted on, an object of motion and rest remains at rest, an object in motion remains in motion at a constant velocity. This first law is also called the law of motion. So let's go ahead and write that down. So this is Newton's first law of motion. An object at rest remains at rest, and an object in motion remains in motion. At a constant velocity. If no net force Excellent. We're just gonna be like that. That's better. Now, an object continues the state of rest or a state of motion at a constant speed along a straight line unless compelled by change by net force. Now, the net force is the vector sum of all the forces acting on the object, which brings us to our example again. So going in with our example, let's say you got this box over here, and it was pushed at this side at a let's say of a force of 4 newtons, and the other person is pushing it that way at a force of 10 newtons. Actually, let me make my arrow a little bit bigger. This means that your net force on this one is your force. Visual forces. So on this one, what you got? You have 10 newtons going to the right, 4 newtons going left. That means your resultant would be 6 newtons going to the right. Okay, let's say we have another example. Let's say if you have this box, let's say if you have a force of 4 newtons going into the right and on top at 3 newtons. Well, your net force having from chapter 3, where you have 2 vectors, head to tail, that means you are going this way. And if you do the angles, if you do the Pythagorean theorem, you should get, let me actually write this down. This is going to be equal to square root 4 squared plus 3 squared, which is going to equal to square root of 25, which equals to 5, which is how much the resultant force would be at a certain angle. And we can tell that you can calculate the angle, so probably angle theta. Now, so inertia is the natural tendency of an object to remain at rest or in motion at a constant speed along a straight line. The mass of an object is the measure of that inertia, and we use kilograms for the unit for the mass. Now that brings us to Newton's second law of motion that states the net force of an object equals the product of the mass and the acceleration of that object. So coming over here, Newton's second law. Your force is going to equal to your mass times your acceleration. A is your acceleration. Which is going to be and distance per time square. Most commonly is meters per second square. Your M is going to be your mass, which is going to be in kilograms. And of course, F, that's your force. Now, looking at this one, having this force, let's talk about this force for a second, which is your mass is in kilograms, and then your acceleration, which we define it as meters per second square. Actually, let me go ahead. Yeah, so you give me like for parentheses, so you get kilograms meters per second square. And that's, ladies and gentlemen, what we give the notation for in Newton, and we give it a big letter N, and that would be our unit for the force. Now, so your force is gonna equal to your mass times your acceleration. Actually, let's look closer. Now, let's go ahead and open up these videos so we can go ahead and see. So in our first video, so in this first video, we have two objects. One of the objects, they're both the same mass, but one of the objects has more force than the other one. Your green force has twice as much as the blue force. Notice that the velocity or the acceleration that contributes to the velocity is increasing. So they both have a velocity that's going in because this little fellow over here has twice as much force than the blue fellow over here. Again, our velocity, our acceleration increases, which increases the velocity for the one with the more force. So basically, when you have a higher force, you will have a higher acceleration. Now, in the second video, they both have the same force on them, but the mass of the green ball is twice as much of the mass of the blue ball. Which contributed, and the blue ball having more velocity. So in this case, solving for the acceleration is going to equal to your force divided by your mass, where if your mass goes up, that means your acceleration goes down, and vice versa. If your mass goes down, your acceleration goes up. Same thing with the force. If your acceleration goes up, if your acceleration goes down, your force. If your force goes down, that means your acceleration goes down. And that's exactly what's happening in this video, as we see again. All right, the third video that we're going to see . Actually, it's not the third video. All right, so what's that? That's the ones we just did. Now, after there was a third video, there was another direction of the force of the video. So in algebraic form, your F equals ma, your force equals your mass times the acceleration. Your F is your force, your m is your mass, and your a is your acceleration. Now, as we see, in the unit of the force is in Newton, which equals to kilogram meters per second square. So let's go ahead and do an example. Find the force needed to serve a 60-gram tennis ball, 30 meters per second. The ball is in contact with the racket for 0.05 seconds. So let's go ahead and write down our information for this question. This is going to be example 2.2. So our mass is 60 grams. Converting into kilograms, so you get 0.06 kilograms. The speed of the ball is 30 meters per second. Now, which speed is this? Final or initial? Well, when you have a racquetball and you hit it from 0 and it goes in at 30. So that should be our final speed, which is 30 meters per second. And our time is 0.005 seconds. And we're looking for the force. Now, in order to do the force, we put in the equation, your force equals mass times your acceleration. We do have the mass, we do not have the acceleration. In order to calculate the acceleration, we use the acceleration equation, which is your final velocity minus your initial velocity divided by your time. And in our case, this is going to equal to your 30 meters per second minus 0 divided by 0.005. And we should get that the acceleration is going to equal to 6,000 meters per second square. That means that our force that we're looking for is your mass times acceleration, which is your 0.06 kilograms times your 6,000 meters per second square, and we should get 6 times 6 is 36, move the decimal, so you should get 360 newtons. So your force is going to equal to 360 newtons. Wonderful. Now let's talk about the weight and the mass. Now, the weight of an object is the force in which the gravity pulls it towards the earth. Now, your weight equals your mass times your gravity. Now, here's a misconception about the weight. When you stand on your scale, the reading that you get is your mass times the gravity pulling you downwards, which means that the reading scale should be in newtons. It's already divided by 9.8. That's why it's showing in kilogram, but the weight is actually measured in newtons, not in kilogram, because again, your weight is your mass times your gravity. Which is the mass in kilograms. Gravity is 9.8 meters per second square. So if you actually do the units, it'd be kilograms meters per second square, which is, again, we define that as the unit of a Newton. If we give it a big letter M. So for example, what is the weight of a 5 kilogram mass? So if your mass was, and this is example 2.10, your mass was 5 kilograms, that means your weight is 5 times 9.8, which equals to 49 newtons. So now let's define something called your normal force. So let's define your normal force. Now your normal force is defined as, which we give it your Fn is the force perpendicular to the surface that exerts on the object. So what does that mean? So let's say supposedly we have a block of ice. Let's say there's some floor over here. Let's say we get a block of ice. This block of ice is standing, which means having a mass for it, it would have a weight. This force, which is your weight, and let's say this is a 5 kilogram object, is going to equal to your 5 times 9.8, which is your 49 newtons. Now, in order for the block of ice to remain stationary, there should be another force going in. That's your normal force going in the opposite side. And I'm just going to go ahead and use this. Here's your normal force. Left. And that's your Fn, your normal force. Which your normal force go ahead. You're having a little problem. Okay, now it's working. So this is going to be your normal force. Now, this is going to equal to 49 newtons, opposite, same value, opposite of your weight. And let me go ahead and write this down. That's our block of ice. That means if we actually take this block and we push it, let's say we pushed it over here, let's say it's right over here. We got your weight still the same. Your normal force. Stayed the same. And then you got, let's say you're going in. At a velocity of 5 meters per second. You still would have the normal force opposing. So from Newton's first law, there is a net force acting on both of them, on both situations. the block of ice is providing the counteracting force in the opposite direction. So as we've seen that the normal force is perpendicular to the surface. So if you have a surface, your normal force would be perpendicular to that surface. And that's your FFN going in this way. And this one, let's say if it's going on an incline and you have a box, so this one will be also your normal force going in as perpendicular to that surface. Now, when we talk about the net force, mathematically, the net force is written as your sigma F. Now, at equilibrium, your sigma F, all your summation of all your forces is going to equal to 0. But we have 3 directions, so that means all your forces in the x direction is going to equal to 0. All the forces in the y direction is going to equal to 0. And all the forces in the z direction is going to equal to 0. Which means this one, that all the forces is going to equal to your mass times your acceleration. Summation of all the forces is going to equal to mass times acceleration. That means, and let me go ahead and write down this in a different color, which means that the acceleration is going to be equal to the summation of all the forces. And again, there's an arrow on top of it because it's a vector. Yes, it's the summation of all the forces divided by the mass. Now, a free body diagram, we will use that to represent the objects and the forces that acts on it. So in this case, let's say you have a car that have 2 people pulling it over. So let's say you got a road. And on this road, you have a car. So this is our little car over here. And you have 2 people pulling it. So let's say pushing it. So let's say this person is pushing at 275 newtons. And you got another person, let me just get over here, pushing the car at 395 newtons. Now, going the car forward, that means you're going to have resistance because of friction. And let's say you're going, the car is going that way with your resistance at 560 newtons. Drawing that in a diagram, here's your X, here's your Y axis. That means you got one of them going that way at 560, and two of them going, and I'm just going to go close to each other. One of them at 395 newtons, the other one is at 275 newtons. So your net force in this case is going to equal to your, so we got the 275 and the 395 are in the positive direction. So we have 275 plus 395 minus 560. So your net force in this case would equal to 110 newtons. Let's say the car mass was 1,850 kilograms. Find the acceleration. That they're doing on this car. Again, using your summation of forces, which is your acceleration over your mass. That means your acceleration is going to equal summation of all the forces divided by your mass. And we found out that summation of all the forces, your net force, summation of all your forces is going to equal to 110. So it'll be 110 divided by 1850. And you should get 0.059 meters per second square. And this is what we just did right now. All right. So we've already been doing this. We got 110 newtons, and the acceleration was 0.059 meters per second square. And this is what we just did. So, and let me go ahead and come back over here. Taking this, your summation for, let's do the X axis, all your forces in the X direction is going to equal all your mass times your acceleration in the X direction. Your forces in the Y direction is going to equal your mass times your acceleration in the Y direction. Your forces in the Z direction is going to equal your mass times your acceleration in the Z direction. So let's do another example, shall we? A man on a raft is the combined mass of the man on the raft is 1,300 kilograms. He is traveling 17 newtons to the east. A wind blows the magnitude of 15 newtons at 67 degrees northeast. Find the X and Y components of the raft acceleration. Ignore the water resistance. So let's go ahead. Here's our example. Now your mass is 1,300 kilograms. So basically, let me go ahead and draw a little diagram of this. He's battling 15 newtons to the north. Let's call this A, which is going to equal to 15 newtons. And he is paddling this way at 17 newtons, and I'm going to call this paddling as P, so which is a resultant. So this is going to be a resultant of your A. So this is your A vector and the x-axis, and your A vector and the y-axis. All right, so looking at the 17 newtons over here, which we call P, notice that there is let's say this is the force, the P force. There is no x-axis. I mean, there's no y-axis. So your FP in the x-axis is going to equal 17 newtons. Your FP in the y-axis is going to equal to 0 newtons. For A in the x-axis is going to equal to, again, from chapter 1, we defined A of y as A sine theta, A of x, this must be labeled x, as A cosine theta. So your FA of x is going to equal to 15 times cosine 67. FA of y is going to equal 15 sine 67, which from these two, your summation in the x direction is going to equal to 23 newtons. In summation in the y direction, this should equal to 14 in newtons, which means that the acceleration in the x-axis is going to equal the summation of your force in the x-axis divided by your mass. So it should be 23 newtons divided by your 1,300 kilograms. So you should get 0.018 meters per second square. Your forces in the y direction is going to equal your summation of the forces in the y direction divided by your mass, and that's going to equal to your 14 newtons divided by 1,300. So you should get 0.011 meters per second square. And that really gets us to Newton's third law of motion, which states that when an object exerts a force on the second object exerts a force on the equal object in the opposite direction on the first object. I always tell my son for every action, there's an equal and opposite reaction. Equal in force, equal in magnitude, opposite in direction. So let's go ahead and watch this little video. So there's a radio control car that's on rollers to demonstrate action and reaction forces. Now, both of them were initially at rest. Moving the car forward, the board go backwards. Moving the car backwards will move the board forward. Now, this would show a diagram of the equal and opposite forces reaction and opposite reaction. So for Newton's third law, So this again brings us, let me go ahead and write this down again. Newton's third law for every action there is a reaction. Same and magnitude, opposite and direction. All right, now let's do the next example, shall we? After we talked about Newton's third law, again, whenever a body exerts a force in second body exerts a force opposite directly, force of equal magnitude on the first body. So for instance, let's say we got an astronaut that's going on a spaceship. The magnitude of the force is 36 newtons. If the mass of the spacecraft is 11,000 kilograms, and the mass of the astronaut is 92 kilograms. What are the acceleration? All right. So let's go ahead and do this example over here. And I'm just going to call this 4.5 because it's slide 4.5. All right, so we got the magnitude of the force is 36 newtons. So your force is 36 newtons. The mass of the aircraft, I'm just going to just say A for the aircraft, at 11,000 kilograms. And the mass of, actually, let me just go space aircraft instead of aircraft in your books. Spacecraft, S, and then MA for astronaut, which is going to be 92 kilograms. And we're looking for their accelerations. Basically, we're looking for the acceleration for the spaceship. We're looking for acceleration for the astronaut. Now, using that, using the equation, where your acceleration is going to equal to your force over your mass. So for the first one, it's going to be 36 newtons divided by your mass, which is 11,000. So you should get 0.033 meters per second squared. On the second, this is the first force over here. On the second force, he's pushing it, so he's supporting the motion. So this force over here is going to be negative. So for the astronaut, this is for the spacecraft. For the acceleration of the astronaut, it's going to be minus 36 divided by the mass of the astronaut, which is going to be your 90. Let me go ahead and write this down. Your force over your mass of the astronaut. So it's minus 36 divided by 92. So this is going to equal to minus 0.39 meters per second squared. And that's what we got. Now, in nature, there are two general types of forces, fundamental and non-fundamental. Your fundamental forces are your gravitational, your nuclear, your electroweak forces. Your non-fundamental is like your friction, your tension in the rope, your normal or your support forces. So every particle in the universe exerts an attractive force on every other particle. A particle is a piece of matter small enough in size to be regarded as a mathematical point. The force that each exerts on the other is directed along with the joining of the particles. Now, when having two objects with, and let me go ahead and ask. Yeah, so you have two objects with mass 1, and there's another object with a second mass. And here's the distance between them. The force that is between them is called the gravitational force. And this is going to equal to some kind of constant, which is g, times your first mass times your second mass divided by the distance squared. G, this is called your gravitational constant, which is 6.67 times 10 to the negative 11 Newton meter square per kilogram square. M1 and M2, that's your mass 1. And M2, that's your mass 2. And R, that's the distance between them. So for instance, if we have M1 at 12 kilograms, M2 at 25 kilograms, separated by 1.2 meters. And we want to find the gravitational force. The gravitational force between them is going to equal to your G M1 M2 over R squared, which is 6.67 times 10 to the negative 11 times 12 times 25 divided by 1.2 squared. And if you do that, you should get 1.4 times 10 to the negative 8 newtons. And this is the definition of the force of Newton's law of universal gravitation. Every particle in the universe exerts an attractive force on every other particle. A particle is a piece of matter small enough to be in size to be regarded as a mathematical point. The force that that each exerts on the other is directed along the line joining the particles. Where Newton's law of gravity states every object in the universe attracts every other object with a force proportional to both of their masses and inversely proportional to the square of the distance between them. And this is the equation that we actually just wrote down, which your gravitational force is G M1 M2 over R squared, where G is your gravitational constant was 6.67 times 10 to the negative 11 Newton meter square per kilogram squared. And we just did this example. And that brings us to the definition of the weight. The weight of the object on or above the earth is the gravitational force that the earth exerts on the object, the weight that always acts downwards towards the center of the earth. On or above another astronomical body, the weight is gravitational force exerted on the object. Because the weight is the mass times the gravity, which the gravity is an acceleration, 9.8 meters per second squared. That means you get kilogram meter squared per second squared, which is going to be your Newton. So having the weight as mass times gravity, and having the weight, which is a gravitational force, is going to equal to G M1 M2 over R squared. Having to use one of the masses. So you got the Earth, which has a mass. Let me actually make it a little bigger. So let's see, you have the Earth, which has the mass of the Earth, which is going to be 5.98 times 10 to the 24th kilogram. And let's see, you got an object on that mass with a mass M. This object has a weight that's going down on the Earth, and the gravitational force which is also a part of the weight because it's a Newton, which is going to be G M1 M2 over R squared, which is in this case is going to be your G, mass of the Earth, times, I'm just going to call it this other mass, M, divided by R squared. So if we made them equal, so G times M1, M-E, mass of the Earth, times M divided by R squared is going to equal to mg. Having to cancel those m's, those masses, that means your gravitational force is going to equal to G times me over R squared, which is going to equal, that's going to mean that G is going to equal to 6.67 times 10 negative 11 times the mass of the Earth that we just put in a little while ago, 5.98 times 10 to the 24th. Divide that by the radius of the Earth square. So this R, let me go ahead, has radius of the Earth, which is going to be 6.38 times 10 to the 6th meter square. Meter. 6.38 times 10 to the 6th. So this is going to be 6.38 times 10 to the 8th meter square. And if you plug all this in, you will get 9.8 meters per second squared, which is the acceleration of gravity. And that's how you calculate the acceleration of gravity. Now, going back to our slides. Again, your gravitational force is going to equal to the gravitational constant times the mass of the Earth divided by the radius of the Earth squared, which again equals to 9.8 meters per second squared. Now, we already defined the normal force, which is the normal force is one component of the force that surface that exerts an object in which is in contact. Mainly, the component is perpendicular to the surface, like we saw earlier. So, for instance, if we had an object that we are pushing on at 11 newtons, and this object has a weight of 15 newtons, that means it has a normal force on it at 15 newtons. That means your summation of all the forces, and in this case, it's going to be in the y direction, there's nothing in the x direction, is going to equal to your 11 is negative. So, and then your 15 is positive, and your 15. So, actually, hold on. Let's make this challenging. Let's make this into what is this normal force. That means summation of the force is going to equal to 0, which means that your normal force minus your 11 plus your 15. I'm sorry, minus 15 because the weight is going down. Is going to equal to 0. That means your normal force minus 26 is going to equal to 0. That means your normal force is going to equal to 26 newtons. All right. Now let's do another example, shall we? Let's say we have, let me get a different color. Let's say we have the same object that has the weight of 15 newtons. And now let's say we are pulling over here by 11 in newtons. What is this normal force that we have? Again, summation of all the forces for equilibrium is going to equal to 0. If you want to go down to it, it's in the y because you're in the y-axis. There's nothing on the x. So on this one, what you're going to have, your normal force plus your 11 newtons minus your 15 is going to equal to 0. That means your normal force minus 4 is going to equal to 0. That means your normal force that needed right now is going to be 4 newtons. All right, now let's talk about friction. Let's go ahead and watch this video.
Do you ever wonder why objects slow down and then stop?
See, when you don't have air on the object, the car is actually cannot slide on the track. But once you put cushion of air under, kind of like the tables of air hockey, and you push the car will just keep on going back and forth because the friction surface is actually to the minimum. So when there's no friction, you will actually keep on going. The friction that will make you stop, roll, or continue. So now let's explain the difference between static friction and kinetic friction. So you got this object that we're about to pull. Now notice on the red arrow over here on our scale to see how much it's going to cost. Now it will be about 23 newtons for to move the object. Once the object moved, notice that the force went down. If you look at the red arrow. And if he's doing it again, notice that once it hits 23, it moves, and then it goes back to 16. That 23, when it goes, that is your static friction. When two surfaces are not sliding across one another, this is called static friction. Static friction is the force that keeps the object at rest. Once the object moves, then you have kinetic friction that keeps on the object, that affects the object moving. Now, your kinetic friction is going to be less than static friction. So when an object is in contact with a surface, there's a force acting on that object. The component of that force is parallel to the surface. It's called frictional surface. Now, when two surfaces are not sliding with one another, the friction is called static friction. Static friction is a force that keeps an object at rest. And the magnitude of static friction forces can have a value of up to 0 of a maximum value. We're going to be talking more about friction when we come to the friction chapter. Frictional chapter. So we're going to be going in this in detail later on in the semester. Now, going back to our forces, your definition of equilibrium. Now, the object in equilibrium, like we said, has 0 acceleration. That means your forces in the x direction is going to equal to 0. Your forces in the y direction is going to equal to 0. So let's say we have this little example over here that we're about to do. Let's say we got a object that has a tension on both sides. So now, before we go in, let me explain something about a tension. The cables and the ropes transmit force through tension. The tension is what pulls out the force to go in until it breaks. Now, so let's say we come back over here. Let's say we got a person with a broken foot. So let's say this is the broken foot over here. Let's say this is his toes right now over there. Okay. And it's tied up to 2 ropes in the hospital. So let's say you got A1 going this way at T1, and you got a tension this way at T2, where your force is going this way. Now, having to do this from chapter 1, this T1 is a resultant of your x and y coordinates, which is going to be your T1 of x, which is going to equal to T cosine. And this is, I think, and the question is 35 degrees. And this is going to be T1 in the y direction, which is T sine 35 degrees. And same thing, let me get a different color. For the second point, let's go ahead and draw my little axes. This is going this way, which is your T2, which is a resultant of your x and your y. So this is going to be your T2 of x, which is going to be T2 cosine 35 degrees, as this is 35 also. And this is going to be your T2y. Now, this is pointing in the negative part, so it'd be minus T sine 35 degrees. That means your sigma F in the X direction, look at the X was going to equal to 0. What are we going to have? You're going to have your T1 cosine 35 degrees plus your T2 cosine 30, is it 35 degrees? Yeah, they're both 35. All right, and then our Y forces for equivalent has to equal to 0, so this is going to have to equal to T1 sine 35 degrees minus T2 sine 35 degrees. And again, this has to equal to 0. All right, that's how you set the equation. And then you just solve the equation for T1 and T2. All right, now let's go ahead and do another example. Let's say we have this object. So let's say you get this as your coordinates right over here. And you got T1 at 10 degrees, T2, and this is making 80 degrees. And again, just a refresher, this little part over here is accumulation of which is this one. With this one, and what you get, this is going to be T1, and what we got, 10 degrees. It's going to be T1 so this is going to be your head to tail, head to tail. This is going to be your T1. This is going to be in the bottom. T1 sine 10 degrees, because again, this is your 10 degrees. And this one over here will be T1 cosine 10 degrees. And for your other point, this one over here, going down, there's going to be accumulation of your first one and your second one. So this is going to be T2 sine 80 degrees. Again, our angle is 80 degrees. And this is going to be the same as this one, which is going to be T2 minus T2 sine. Yeah, this is the x-axis, supposed to be cosine. Sine 80. Where your sigma forces in the x direction is going to equal to T2 sine 80 minus T1 sine 10 is going to equal to 0. We're going to call this equation number 1. For equation number 2, your sigma forces in the y direction is going to equal to T1 cosine 10 minus T2 cosine 80 minus W is going to equal to 0. That's equation number 2. Now we're going to take equation 1 and solve it for T1. That means solving for this, T1 is going to equal to T2 sine 80 divided by sine 30. Right there, I'm sorry. We're going to call this equation number 3. We're going to sub equation number 3 into equation number 2, which again, here's our equation number 2 over here. I'm sorry, here's our equation number 2 over here. Here's equation number 1. So we're going to sub it into equation number 2. So that means your sine 80 divided by sine 10, T2 cosine 10 minus T2 cosine 80 minus your work is going to equal to 0. This means that T2 is going to equal to the work divided by sine 80 divided by sine 10 times cosine 10 minus cosine 80. Now, our work, we're going to say is 3150 newtons. This means our T2 is going to equal to 582 newtons. I just reversed them. All right, this unfroze again. That means your T2 is going to equal 582 newtons. Substituting that into the first one, that means T1 is going to equal to 582 times sine 80 divided by sine 10, which equals to 3.3 times 10 to the 3 newtons. All right, let's do one last example, shall we? So let's go back over here. Yeah, supertanker F mass of 1.5, and they're being towed by 2 tugboats. The tension term 110 is equal in degrees of 30 degrees with respect to tanker X. The engine produces a forward drive D at 7.5 times 10 to the 3 newtons and a reversal of 40 times 10 to the 3 newtons. Tanker moves forward with an acceleration of 2 times 10 to the -3. Find T1 and T2. Basically, this is our tugboat over here. So let's go ahead and draw this analysis over there. So this is an example, and this is going to be non-equilibrium example. Now so you have a tugboat is your tugboat that has two tensions, T1 and your T2. This is creating an equal degrees of 30 degrees. Of course, you're having your reverse R over here, and over here you got your D drive on there. And having to analyze T1 and T2. T1 is a resultant of T1 cosine 30 degrees and T1 sine 30 degrees. Same thing with the T2. We solved this a little while ago. This is going to be minus T2 sine 30, T2 cosine 30 degrees. Use over 30 degrees, which again, this is the same as this one over here. So now we analyze it. Your sigma forces in the x direction, which equals the MAX, all the mass times the acceleration in the x direction. Now, so we're going to be looking at the x direction. That means your T1 cosine 30 plus T2 cosine 30 plus your drive force minus your R force equals to MAX. And let me go ahead and label this. So this one is going to be 7.5 times 10 to the 3 newtons. This one is going to be 40 times so your mass is going to be, for this one, 1.5 times 10 to the 8 kilogram, which means that our forces in the x direction is going to be MAX, again, which is going to be T1 cosine 30 plus T2 cosine 30 plus D minus R is going to equal to M. Write down better R than that. MAX, that's our first equation. Looking at the Y right now, what are we going to have? We're going to have your T1 sine 30 minus T2 sine 30. We don't have any, this is only in the x direction, it doesn't affect in the y direction. So it's going to equal 0. This is going to be equation number 2. Which means take equation number 2. What you're going to have? You're going to have to T1 sine 30 is going to equal to T2 sine 30. That means your T1 is going to equal to T2, and this is going to be equal equation number 3. And we're going to call that the T. So both tensions are going to be the same, so we're just going to give them one name tension. So we're going to sub the third one into our first equation. So basically your 2T cosine 30 is going to equal MAX minus D plus R. That means T is going to equal to MAX minus D plus R over 2 cosine 30. And this is going to equal to 1.5 times 10 to the 5th Newton. And that should close chapter 4 for the Cutnell and Johnson book. If you have any questions, please email me at abunaem@gmail.com. Thank you so much.